Okay, so this time we want to look at the notion of a limit for a complex function. So this is sort of the first step in looking at extrapolating the theories of calculus into what we know about the complex algebra and some of the very elementary complex functions which we have discussed in the past. So the idea of a limit that we've discussed typically in single variable calculus involves some limit with a limiting variable going to some limiting value or limiting input, which you could call a, of some function f of x. And then we extrapolate this notion to multivariable calculus, taking the limit as x1 all the way up to x sub n goes to some a sub 1 all the way up to a sub n. And then this is of a function of f of x1 all the way up to x sub n. And we've discussed how to take limits in single variable calculus. We've discussed how to take limits in multivariable calculus. It's really going to be the same sort of thing in the complex calculus and complex analysis. So that's what we want to do today. We're not going to belabor the point because we know how epsilon delta proofs work, but we will kind of cover just the notion of what it looks like in the sort of complex recipe. So we'll start by discussing the notion of a limit of a complex sequence, and this really comes down to the generalized notion of precise convergence. So here's a definition. We'll have two definitions today, and then that will be it. Definition: a sequence of complex numbers, z sub n, as 1 goes to infinity, has the limit z naught such that z sub n approaches z naught as n approaches infinity. If for any epsilon greater than 0, there is some integer n such that z minus z naught is less than epsilon for all n greater than n. Right? So basically what this says is, okay, well, if I pick any sort of epsilon or any sort of n, I can always find an epsilon that's going to be satisfying this problem. So this is the notion of a sequence, and essentially, what this is saying is we're saying that if I have a disk in the complex plane, so if I have a disk, and this is going to be a random disk, it can be wherever we want it to be. So there's a disk. And we're going to have some sequence, and this sequence is going to be coming in however we like it to, and maybe it converges, and then there's going to be a lot of points around this point at z naught. So this means that each term, z sub n, for little n bigger than big N, will lie in some open disk of radius epsilon around z naught. So that's essentially what this proof, this epsilon idea means. And if you've studied real analysis or considered maybe AP calculus, get into the really nitty-gritty with the studies of convergence, you would come up to this topic. But for complex analysis, it's really the same sort of proof. It's just you need to be careful about the complex numbers, the imaginary unit, and just some more of the nuances. So for example, if I were to ask, like if I were to ask the limit as n approaches infinity of, let's say, I don't know, I over 3 to the n, if I asked I over 3 to the nth power, what we can say is we can use the absolute value, and this would go to the limit of 1 over 3 to the n. And we can see that that's 0, so we'd converge absolutely, and then there you go. But there are other examples where you might have some sequence like the limit as n approaches infinity of just I to the n. And of course, this is a little bit more nuanced because when you take I to the n, what you end up doing is you end up taking a unit circle and you end up rotating around it. So actually, this is like this is one of the cases where you have like almost an alternating sequence. And of course, that has no solution and it does not converge or have a limit. Now, a similar concept that we can discuss is a limit of a complex valued function. So we can look at another definition, which will look a little bit more like the single variable calculus definition, quite similar. So definition, let f be defined in the neighborhood of z naught. The limit of f of z approaches z naught, as z approaches z naught, is w naught if for any epsilon larger than 0, there exists some positive delta, such that for f of z minus w naught, there, whenever 0 is less than modulus of z minus z naught is less than delta. So again, we can look at a geometric argument. So it says that any neighborhood of the limiting value w naught is going to have all the values assumed by the function in the neighborhood of z naught, except for possibly at z naught. So we're still going to be able to kind of make that convergent sort of definition. So of course you can take all of these limit definitions, the epsilon delta proof, the epsilon proof for convergence, and do what you want with it. It's very similar to what you would deal with treating calculus more rigorously, or how you would deal with limits in multivariable calculus. It's very similar. So all of those proofs transform over to complex variables. So we won't do an example for this. Anyways, in the next video, we want to explore how when we look at the notion of continuity, it's going to bring to light a lot of very, very similar properties that we have between the real calculus and the complex calculus. We're going to see that it makes our lives a lot easier when dealing with the notion of the calculus-based operations like your derivative or your integral. So that's all to come. So thanks for watching, and we will see you next time.